So, hi everyone. In this part of the course, we are going to start the technical part. We are going to introduce the notion of a non-commutative probability space. This is where our random variables will live. And as you'll see, it's an abstraction of random variables. You won't see a priori probability measures or anything of analytic nature. You're only going to see random variables sitting there with their powers. So we are going to see an algebra. We can add and multiply random variables, and we are going to encode the moments of the distribution by a certain machinery, which is essentially functional with some properties. So let's get right to it. Okay, so this part about non-commutative probability spaces is heavily based on the course book, which is the Nika Speicher book. Particularly, it's the first chapter there. Okay. So, as I said, I'm going to assume this course is for theoretical computer scientists, so I'm not going to assume you know much or anything about, or at least maybe you have seen it, but don't. It's like that your working knowledge about algebras and so forth. So let me start by defining the notion of a C algebra. So C algebra, where C is just the complex numbers, is first of all, it's a vector space. It's a vector space over C, okay? Namely, you can add elements in the algebra, like vectors, and you can multiply them by complex numbers, like scalars. But you can also multiply the the elements themselves in the algebra. If you have matrices in mind, that's a good example. Namely, there is an operation which is a product operation that takes an element or two elements from the set, from the algebra, and produces a third element. And that element you should think of as a product. And as usual, you want the product and the addition to behave well with each other. So we're going to assume left and right distributivity. So that's what's in here. Namely, the sum times the product times C is distributed accordingly. So it's A times C plus B times C. Because we are non-commutative, we're also emphasizing the fact that we have both left and right distributivity. And also we have compatibility with scalars, right? I mean, we already have a product of an element from the algebra with an element from the field, the complex field, and we want to the new product to be compatible with the usual scalar product. And by that, I mean that if you take, a complex number alpha, it's a scalar, times A from your algebra, and you take the product, the new product that you define, of beta times B, where again, beta is from the complex numbers and B is an element of the algebra, but that's the same thing as first taking the scalar product and then taking that new scalar and taking its product, scalar product, with this vector, with this element of the algebra, which is obtained by the product, the new product. Okay, so that's generally a C algebra. Some people assume, and we are going to be those some people, associativity. So associativity just means that you don't need brackets, right? The order, you don't need the order from left to right matters, not the order in which you apply the products. And we are also going to assume that we have a unit with respect to multiplication, to the new multiplication that we have. Okay, so that, namely, the name for it is that A is unital, but it really just means that there exists an element which we denote by 1 and sometimes 1 subscript A, which is identity under multiplication, both left and right. And once you have that, by the way, you can always embed the complex numbers within your algebra, because you can think of, for a complex number alpha, now this becomes an element of your algebra, and this way you can identify the complex numbers as part of your algebra, okay? Okay, so that's a C algebra. It's essentially a vector space with product, okay? And there is an identity with respect to that product. Um, so so in a second you'll see, but that part is going to be so our random variables are going to have the structure of a C algebra. So the elements in the C algebra are going to be the random variables, and now we want something that resembles expectation, okay? Because we are going to work with moments, and the moment is the expectation of a power, right? So the powers are, encoded within the algebra, and now we need the expectation operator. And we abstract this as well. So a linear functional is this kind of function. Generally, a linear functional looks like that, but in the context of an algebra, it's a function from the algebra to the complex numbers, and it respects the addition of the underlying algebra. Namely, if you take phi of sum or scalar sum, like alpha a plus beta b, then it should be equal to alpha phi of a plus beta phi of b. And also, if a is unital, and a will always be unital in all of our cases, then we see that phi is unital if it all respects identity. Namely, it sends one of the algebra to the usual one of the complex numbers. Now note that linear functional does not respect product, namely the new product that we have, and phi of a squared is not necessarily phi of a squared, right? That's the whole point. The point is that phi is going to encode information about the powers. So if phi of a squared were equal to phi of a squared, phi wouldn't be it wouldn't be a good tool to encode all the different powers. Again, and on this you can think as a kind of linearity of expectation and so forth. But the powers we want, the whole point is that phi encodes information about the power, so we don't want the linear function to respect the product. Okay. Okay, now we're ready for the main definition. So a non-commutative probability space, and NCPS for short, is just a pair. It's a unital C algebra, A, the random variables, and a unital linear functional from A to C. That's the expectation. Okay, and because of that, the elements are called non-commutative or just random variables, non-commutative random variables. And again, you should think of phi as an expectation. Phi of A, you should think of it in a sense, and you will see example, as the expectation of A. Now, in many cases, phi is going to have a property that will be useful for some of the proofs that we will need, and that's triviality. So a non-commutative probability space is said to be trivial if phi of AB is phi of BA. Okay, so you can kind of use a kind of cyclic, change cyclically in a cyclic manner the argument of phi, and the value stays the same. Now, it's not that AB equals BA, right? It's just that phi of AB equals phi of BA. The random variable is not necessarily commute. And just as a warning, it doesn't mean that, you can permute everything however you want within phi and it will stay the same, right? So for example, phi of ABC is phi of CAB because you can just take this C here, and you can do it again. Now you can take the B before the element CA, so it gets BCA. So phi of ABC is the same as phi of CAB and the same as phi of BCA, but it's not necessarily the same as phi of BAC. Right? Only cyclic permutations are allowed, not any permutation. Good. So most of our non-commutative probability spaces are going to be trivial. Now, on top of that, and again, I'm kind of, we started with the basic non-commutative probability space definition, but I want to add structure to it because that structure is going to be there and is going to be useful in our examples. So in many cases, we are going to have a star operation, like a conjugation in a sense. So this definition is about the algebra. It doesn't refer to the linear functional. So say you have a C algebra. So it is going to be called a star algebra if on top of the product that you just defined, you also have another operation called a star operation, which takes one element, produces one element, and it just, by that rule, that just stars it. And that star operation should have two properties. It should be antilinear and should be an involution. By antilinear, I mean this thing, which you're familiar with. And by involution, I mean that when you apply the star twice, you get the same element again. Okay, so you've seen that, right? For example, for matrices, you have the star operation. For complex number, you have conjugation. Right. Good. So that's in the level of an algebra. A star algebra is an algebra that is equipped also with a star operation. Now, if you have a non-commutative probability space, namely you also have this phi, and assuming that A has the structure of a star algebra, then assuming the star behaves nicely with respect to phi, namely assuming that for every element in your algebra, phi of A star A is real, usually it's complex, and non-negative, in that case, we are going to say that phi is positive, or non-negative if you want, and the pair A sub phi, A phi is not just going to be called a non-commutative probability space, but a star probability space, because no one wants to say a star non-commutative probability space. All right, so a star probability space is a non-commutative probability space in which the underlying algebra is a star algebra, so you have this extra operation, and it behaves nicely with phi in the sense that phi of A star A is this zero. And that's probably familiar to you. I mean, this sounds like positive in a way, right? So for example, if you have a matrix and you look at this matrix, then that's a positive semi-definite matrix, right? So all its eigenvalues are non-negative, which is an example. We'll see the examples, but it seems related, and it is indeed a special case of a star algebra. Okay. So that's the notion of a star algebra. Of a star probability space. And in a star probability space, there are some special elements. The most special is the self-adjoint element. So an element A in the star algebra will be called self-adjoint if it equals its star version. That for matrices, for example, that just means the matrix is symmetric or Hermitian, but essentially symmetry. Connecting to the introductory part, these are like the underrated graphs. You also have unitary elements. So what's a unitary element? Well, you can define it algebraically as saying that A commutes with its star, and not only that, their product is one, right? Okay, so that's an algebraic way of saying what unitary is. By the way, if you remember that we talked about the spectral decomposition, we said that every symmetric matrix can be written as you can decompose it. It has so anyhow, you can write it like that. I didn't quite say it this way, but it's essentially the same thing. So I wrote it not in matrix product form, but in a kind of, I expanded it. But so every self-adjoint, if this is self-adjoint, then what you can show is that there are unitaries, unitaries. You can change the order of the rows such that A can be written as a unitary, a diagonal matrix, and then the conjugate of the unitary, or the transpose in that case of the unitary. So unitaries and self-adjoint elements are related to each other in that sense. Anyhow, the third type of element, which actually is a generalization of the first two, is a Norman element. So a normal element is an element in which commutes with its star, but it doesn't have to necessarily be, the product doesn't have to be one. And that's actually a very interesting thing, because normality in matrices is, you can either define a matrix to be normal if this hold, or you can define it to be normal if it has an orthonormal basis of eigenvectors. That's kind of the geometric way of viewing normality, right? So it's, and I actually was more used to that than to that, right? So in a sense, this is how you think about normal metrics, and this is how you sometimes prove things about normal matrices, because algebraically it's nice, a nice identity to have. So it's nice that this geometric definition can be encoded kind of purely algebraically. Okay. Okay. So in the homework exercise, you'll show that many things happen. So for example, or expect to happen. So for example, phi applied to A star is going to be the conjugate of phi of A, right? And another thing, so that was sensible. It's not so easy to prove, by the way, but there is a guided exercise question in homework. And secondly, you have a generalization of the Cauchy-Schwarz inequality. Namely, if you take phi of B star A, so that's a complex number, and you take its modulo, like its size and square, then that's at most the phi of A star A, phi of B star B. So it looks like a Cauchy-Schwarz, but it's not clear where is the inner product. It's kind of implied by that. So you may imagine that maybe you can define an inner product like that, which is sensible, of course. And it actually works essentially. I mean, it's bilinear, and because of that, you have the conjugation when you change order and so forth. But it's not quite an inner product, because there may be an element B that its inner product with every A is zero, in particular with itself, and it's a non-zero element. So there is some kind of degenerate, there are examples where this gives you a kind of a pseudo inner product, something that is a bit degenerate in that sense. But never mind, it is a good idea to think of this as an inner product of sort. And in fact, we are going to define and usually exclude the fact that phi has this annoying property. So if a phi is a star probability space, then you are going to say that phi is faithful, not sure what's the origin of the name, if whenever phi of A star A is zero, remember it's always at least, it's real and it's at least zero, right? But whenever it's zero, it implies that A is zero, right? Which is what you expect from an inner product. Because the inner product of A with itself, it's essentially the size of A, the norm of A squared, the induced norm of A squared, and the norm should be zero only when the element is zero. Okay. So in all of our cases, I think phi is going to be faithful. So it's not harmful to assume that already from the get-going. And note that indeed, if phi is not faithful, then phi doesn't really capture all the information. So, for example, if phi is not faithful, then there exists an A such that, well, phi of A star A is zero. But if you remember the Cauchy-Schwarz inequality, which you will prove, right? This is zero for any B. So this means that this is zero. And so, if there exists an A for every element B or B star, but you can star it again, you get that phi of BA is zero, then this means that kind of A makes phi degenerate, right? You can't learn anything. Once you take the product with A, kind of all the information that lies in phi vanishes. So that's kind of another reason to include into our abstraction the fact that we want phi to be faithful. Okay. So again, the point is we are trying to find kind of the right abstraction for non-commutative random variables, especially in the setting where we want to work with moments. So we want the powers to be there. We want something that measures of the expectation of a power. And we want to abstract properties of expectation that we like linearity, of course, but also things like that, like faithfulness and tracial, being tracial, and so forth. Okay, so